Your standard tester showing open grounds indicates a potential issue with the grounding system. In a properly grounded system, there should be a continuous path from outlets to the electrical panel's grounding electrode. However, since the GFCI tester does not trip on the GFCI outlet, it suggests that there may be an alternative grounding path through the neutral wire. This is known as bootleg grounding and is not a safe or reliable method of grounding. The linked downline outlets that are protected by the GFCI outlet are considered to be downstream of the GFCI. As long as the downline outlets are properly wired and the GFCI outlet is functioning correctly, they should be protected from ground faults even without a dedicated ground wire. However, it is important to note that this protection relies solely on the proper operation of the GFCI outlet. The open ground should be investigated further. An experienced electrician should test the grounding system to determine the actual grounding condition. While the downline outlets are currently protected by the GFCI outlet, it is recommended to install dedicated ground wires for all outlets, including those downline of the GFCI. This will provide a more reliable grounding system and reduce the risk of electrical shock in the event of a fault. The presence of water, for example, from humidifiers, can potentially increase the risk of electrical shock, even if outlets are GFCI protected. The use of GFCI protected outlets should not be considered a substitute for proper grounding. Any electrical repairs or upgrades should be performed by a qualified electrician to ensure safety and compliance with the electrical codes. Let's delve into the specifics of GFCI protection and grounding in older electrical systems. The observations made during the home inspection highlight some crucial points regarding electrical safety. Let's start by understanding the role of grounding in an electrical system. Grounding provides a low impedance path for fault current to return to the source, typically the electrical panel. This path facilitates the rapid tripping of a circuit breaker or fuse, interrupting the flow of electricity and preventing potential electrical shock hazards. A properly grounded system ensures that metallic parts of appliances and electrical equipment are at or near ground potential. This minimizes the risk of electric shock if a fault occurs and a live wire comes into contact with a metal enclosure. Now, in the situation described, the standard tester indicates open grounds, suggesting a break or discontinuity in the grounding path. This could be due to several factors, including corroded connections, loose wiring, or a complete absence of a grounding conductor. It is important to note that the absence of a ground wire does not necessarily mean that the circuit is unprotected. GFCI outlets can provide a level of protection against electrical shock in the absence of a dedicated ground wire. GFCI outlets work by monitoring the current flowing into and out of a circuit. If there is an imbalance of even a few milliamperes, indicating a leakage current potentially flowing through a person to ground, the GFCI outlet will trip, interrupting the power supply in a fraction of a second. This rapid response can prevent serious injury or even death. However, relying solely on GFCI protection without a proper grounding system has limitations. Firstly, GFCI outlets only protect against ground faults, which are electrical faults where current flows to ground through an unintended path. They do not protect against other types of electrical faults, such as short circuits or overloads. Secondly, GFCI outlets can fail over time, and their effectiveness can be reduced by factors such as voltage surges, moisture, and physical damage. Therefore, it is recommended to install dedicated ground wires for all outlets, even those protected by GFCI outlets. This provides a more robust and reliable grounding system, offering greater protection against electrical shock hazards. Now, let's address the issue of bootleg grounding. Bootleg grounding is a dangerous practice where the ground terminal of an outlet is connected to the neutral wire. This creates an alternative grounding path through the neutral wire, which can appear to provide a ground connection when tested with a standard tester. However, bootleg grounding is not a safe or reliable method of grounding. Under normal conditions, the neutral wire carries current back to the source, the electrical panel. If there is a fault in the circuit, the neutral wire can become energized, potentially exposing anyone who touches a metal part connected to the bootleg ground to a dangerous voltage. Furthermore, bootleg grounding can interfere with the proper operation of GFCI outlets. GFCI outlets rely on detecting small differences in current between the hot and neutral wires. If there is a bootleg ground, some of the fault current may flow through the neutral wire, reducing the current imbalance and preventing the GFCI outlet from tripping. This can leave individuals vulnerable to electrical shock. In the described scenario, the fact that the GFCI tester does not trip the GFCI outlet suggests the possibility of bootleg grounding. The GFCI tester works by injecting a small amount of current to ground. If there is a bootleg ground, the current may flow through the neutral wire instead of to ground, preventing the GFCI outlet from tripping. However, the fact that the test button on the GFCI outlet does trip the outlet indicates that the GFCI function itself is working. The test button simulates a ground fault, causing the GFCI outlet to trip and interrupt the power supply. So, to summarize, the observations made during the home inspection indicate a potential issue with the grounding system. The open grounds suggest a break or discontinuity in the grounding path, while the non-tripping of the GFCI tester raises concerns about bootleg grounding. Although the GFCI outlets provide a level of protection against electrical shock, they should not be considered a substitute for proper grounding. It is recommended to install dedicated ground wires for all outlets, even those protected by GFCI outlets. From a home inspector's perspective, the situation should be noted in the inspection report. The report should state that the open ground should be investigated further by an experienced electrician. The electrician should test the grounding system to determine the actual grounding condition and identify any potential hazards. The report should also recommend the installation of dedicated ground wires for all outlets, including those downline of the GFCI outlets. This will provide a more reliable grounding system and reduce the risk of electrical shock in the event of a fault. In addition, the report should emphasize the importance of having any electrical repairs or upgrades performed by a qualified electrician to ensure safety and compliance with electrical codes. Finally, the report should mention the potential risk of electrical shock in the presence of water, even if outlets are GFCI protected. The use of humidifiers and other water-containing appliances can increase the risk of electrical shock, especially in areas where outlets are not properly grounded. Therefore, it is crucial to exercise caution when using electrical appliances near water and to ensure that all outlets are properly grounded and GFCI protected. Let's address some of the technical aspects of grounding and GFCI protection in more detail. Grounding is achieved by connecting the metal parts of electrical equipment to a grounding electrode, which is typically a metal rod driven into the earth or a metal water pipe that is in direct contact with the earth for at least 10 feet. The grounding electrode provides a low impedance path for fault current to return to the source, facilitating the rapid tripping of a circuit breaker or fuse. The size of the grounding conductor is determined by the size of the circuit conductors. The National Electrical Code, NEC, provides specific requirements for grounding conductor sizes in Table 250.122. For example, for a 20 amp circuit, the minimum size of the grounding conductor is 12 American wire gauge, UG, copper. GFCI outlets are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The NEC requires GFCI protection for all 125-volt, 15 and 20 amp receptacles installed in these locations. GFCI outlets are also required for certain appliances, such as dishwashers and washing machines. GFCI outlets are available in two types: receptacle type and circuit breaker type. Receptacle type GFCI outlets are installed in place of standard outlets, while circuit breaker type GFCI outlets are installed in the electrical panel. Both types of GFCI outlets provide the same level of protection against electrical shock. The testing of GFCI outlets should be performed regularly to ensure that they are functioning properly. The test button on the GFCI outlet should be pressed monthly to verify that the outlet trips and interrupts the power supply. If the GFCI outlet does not trip when the test button is pressed, it should be replaced immediately. The use of GFCI testers is another way to test GFCI outlets. GFCI testers simulate a ground fault, causing the GFCI outlet to trip if it is functioning properly. However, It is important to note that GFCI testers can give false readings if there is a bootleg ground or other wiring problems. Therefore, it is always best to have an electrician inspect the wiring if there are any concerns about the proper functioning of GFCI outlets. In addition to grounding and GFCI protection, there are other safety measures that can be taken to reduce the risk of electrical shock. These measures include using properly insulated electrical cords, avoiding the use of extension cords whenever possible, and keeping electrical appliances away from water. It is also important to educate children about electrical safety and to teach them not to play with electrical outlets or appliances. By taking these precautions, the risk of electrical shock can be significantly reduced. Now, let's discuss the specific issues raised in the home inspection scenario in more detail. The fact that the standard tester showed open grounds indicates that there is a break or discontinuity in the grounding path. This could be due to several factors, including corroded connections, loose wiring, or a complete absence of a grounding conductor. The electrician should inspect the wiring to determine the cause of the open grounds and make the necessary repairs. The fact that the GFCI tester did not trip the GFCI outlet suggests the possibility of bootleg grounding. The electrician should inspect the wiring to determine if there is a bootleg ground and correct the problem. The electrician should also verify that the GFCI outlet is properly wired and functioning correctly. The recommendation to install dedicated ground wires for all outlets is based on the fact that this provides the most reliable grounding system. While GFCI outlets can provide a level of protection against electrical shock in the absence of a dedicated ground wire, they should not be considered a substitute for proper grounding. The installation of dedicated ground wires will ensure that all outlets are properly grounded and that the risk of electrical shock is minimized. The presence of water can increase the risk of electrical shock, even if outlets are GFCI protected. Therefore, it is important to exercise caution when using electrical appliances near water and to ensure that all outlets are properly grounded and GFCI protected. The electrician should inspect the wiring to ensure that it meets all applicable electrical codes and safety standards. The electrician should also provide the homeowner with information on electrical safety and how to properly use and maintain electrical appliances. By addressing these issues, the homeowner can ensure that their electrical system is safe and reliable. Let's consider the National Electrical Code or NEC requirements related to the situation. NEC Section 250.4 addresses grounding and bonding requirements, emphasizing the need for a low impedance path to facilitate the operation of overcurrent devices. This section highlights the importance of a properly installed grounding electrode system, as well as the bonding of metallic enclosures and equipment. NEC Section 210.8 covers GFCI protection requirements for dwelling units. This section specifies the locations where GFCI protection is required, such as bathrooms, kitchens, and outdoor areas. NEC Section 406.4 addresses the replacement of receptacles. This section allows the replacement of two-prong receptacles with GFCI protected receptacles under certain conditions, such as when a grounding means does not exist in the receptacle enclosure. However, this section also requires that the GFCI protected receptacle be marked with the label No Equipment Ground. The NEC also addresses the use of arc fault circuit interrupters, or FSIs, which provide protection against arc faults, which are a common cause of electrical fires. FSIs are required in certain locations, such as bedrooms and living rooms. In addition to the NEC, there may be local electrical codes that apply to the situation. It is important to check with the local building department to determine if there are any additional requirements. The electrical system should be inspected by a qualified electrician to ensure that it meets all applicable codes and safety standards. Let's talk about what an electrician may do if called out to inspect a situation like this. Firstly, they will perform a visual inspection. The electrician will visually inspect the wiring, outlets, and electrical panel to identify any obvious problems such as damaged wiring, loose connections, or overloaded circuits. Secondly, they will test the grounding system. The electrician will use a variety of test equipment to verify that the grounding system is properly installed and functioning correctly. This may include testing the resistance of the grounding electrode system, as well as testing the continuity of the grounding conductors. Thirdly, they will test the GFCI outlets. The electrician will use a GFCI tester to verify that the GFCI outlets are functioning properly. This may involve tripping the GFCI outlet with the test button, as well as using a GFCI tester to simulate a ground fault. Fourthly, they will check for bootleg grounds. The electrician will use a multimeter to check for bootleg grounds. This involves measuring the voltage between the ground terminal and the neutral terminal of the outlet. If there is a voltage present, it indicates that there may be a bootleg ground. Fifthly, they will make repairs as necessary. If the electrician identifies any problems with the electrical system, they will make the necessary repairs. This may involve replacing damaged wiring, tightening loose connections, or installing new outlets. Sixthly, they will provide recommendations. The electrician will provide the homeowner with recommendations on how to improve the safety and reliability of their electrical system. This may include installing dedicated ground wires for all outlets, upgrading the electrical panel, or installing R fault circuit interrupters. Lastly, they will provide documentation. The electrician will provide the homeowner with documentation of the work that was performed, as well as any recommendations that were made. This documentation can be used for insurance purposes, as well as for future reference. Let's also consider the long-term implications of electrical safety. Ensuring electrical safety in homes, especially older ones, is not just a one-time fix but an ongoing commitment. Regular inspections, maintenance, and upgrades are crucial to prevent potential hazards. Homeowners should be educated on basic electrical safety practices, such as not overloading circuits, using extension cords safely, and recognizing signs of electrical problems like flickering lights or burning smells. It's also vital to keep up with advancements in electrical technology and safety standards. For instance, arc fault circuit interrupters of size have become increasingly important in preventing electrical fires, and understanding their function and proper installation is essential. Moreover, the increasing use of electronic devices in homes necessitates a robust and reliable electrical system. Over time, older wiring can degrade and become unsafe, so upgrading the electrical panel and wiring may be necessary to accommodate the demands of modern appliances and electronics. In addition, homeowners should be aware of the potential hazards associated with water and electricity. Simple precautions, such as keeping electrical appliances away from water sources and using GFCI outlets in damp locations, can significantly reduce the risk of electrical shock. Furthermore, proper grounding is essential for protecting against electrical faults and ensuring the safe operation of electrical equipment. In conclusion, electrical safety is a multifaceted issue that requires attention to detail, adherence to codes and standards, and a commitment to ongoing maintenance and upgrades. By addressing the issues identified in home inspections and by following the recommendations of qualified electricians, homeowners can create a safe and reliable electrical environment for themselves and their families. We can also consider some additional scenarios related to electrical inspections in older homes. In some cases, older homes may have knob and tube wiring, which is an outdated wiring method that is no longer considered safe. Knob and tube wiring consists of single insulated wires that are run through porcelain knobs and tubes. This type of wiring is prone to damage and can be a fire hazard. If knob and tube wiring is present, it should be replaced with modern wiring methods. Another issue that may be encountered in older homes is aluminum wiring. Aluminum wiring was used in some homes in the 1960s and 1970s. Aluminum wiring is more prone to corrosion and can become loose at connections, which can create a fire hazard. If aluminum wiring is present, it should be inspected by an electrician and repaired or replaced as necessary. In addition, older homes may have undersized electrical panels. An undersized electrical panel may not be able to handle the electrical load of modern appliances and electronics. If the electrical panel is undersized, it should be upgraded to a larger panel. Furthermore, older homes may have outlets that are not properly grounded. Ungrounded outlets can be a shock hazard. If ungrounded outlets are present, they should be replaced with GFCI protected outlets or grounded outlet. It's also important to check the condition of the service entrance cable, which is the cable that brings electricity from the utility company to the home. The service entrance cable should be inspected for damage and replaced if necessary. In addition to these issues, it's important to check the condition of the smoke detectors and carbon monoxide detectors in the home. Smoke detectors and carbon monoxide detectors should be tested regularly and replaced if they are not functioning properly. Finally, it's important to educate homeowners about electrical safety and to provide them with information on how to properly use and maintain their electrical system. By addressing these issues, the safety and reliability of electrical systems in older homes can be improved.